Okay, sorry about that. The connection, the stream got disconnected. I have a little bit problem of unstable internet. Okay, and this has happened multiple times. So I know it's frustrating, but okay. And so we were discussing the speed of the moving rope. And at any time t, let us suppose it's v of t, that will equal to g times t. And we assume that the distance fallen by free end is suppose our y of t, so that will be equal to half gt square. And for this we can just draw an approximate figure. So this is our, and like I said, that the distance followed by the rope is now y of t. Okay. So it means this is the level of the support. So this entire distance is our y, basically y of t. For the sake of simplicity, we are going to write only y. But the length of the rope will be equally divided into two halves. Okay, this will be our left half and this will be our right half. So let us suppose this length is our x. Okay, ignoring the covered path, we are just going to ignore, and we are going to assume that the entire length below the table is x. So this will be x, as well as on the second part also our x. So total length is our y of the rope that is below the table, and based on this we can write the relationship between x and y. Okay. So we can say that the length of the rope hanging below the table, that is our x of t, and that will be our half of y of t. Therefore we can write that our x of t is equal to our gt square divided by 4. Okay. And once again we are going to divide this rope into two parts. First will be a moving rope and other one will be a stationary part. Or we can say parts of the rope. And in these parts of the rope, we are saying at time t. So first is our stationary rope. Or we can say hanging at rest. So under this condition we are going to get its length, which I have said is our x, and that is equal to gt square by 4. And we are going to find out what is the weight. Let us call this as our F1, and that will be equal to lambda gx, which comes as our lambda g square t square by 4, substituting value of our x. And the second one will be our moving rope, which is still falling. Moving rope or we can say still falling, and its length we can easily calculate. So we can say its length, total length was our L, so this comes as L minus X, and its speed will be equal to our G times T. Therefore, we can find out the momentum of the moving rope. So we can say that momentum of moving rope, which is our P, and this P will be equal to our minus lambda L minus X times GT, and downward we are going to take a negative sign because of the downward movement. Now we are going to use our Newton's law with respect to momentum, that is the summation of the forces is equal to rate of change of momentum. Okay, and so we are going to say for whole rope, you can write that a summation of the forces is equal to our rate of change of momentum, and forces on the rope will be weight downward and support, that is normal, upward. Okay. So because we are interested in this force F, therefore you can say that forces on the rope, so we are going to have our weight, that is our lambda Lg, and it will be downward, and we having support force, which is our normal, and this is upward. Therefore, we can write the equation that our normal minus downward force will be our rate of change of momentum, that is our minus lambda L minus X, and this comes as GT. Now we simply differentiate it, and we can write that, okay, let me solve it separately because it will be multiple variable differentiation. So we can say that our d of dt minus lambda L minus X G of t. So we get this as minus lambda Lg plus lambda Gx plus lambda Gt dx by dt, and we substitute value of our x we already know, that is our x is equal to gt square by 4. So we get this as dx of dt will be equal to gt by 2. Now we substitute it and we get our rate of change momentum, that is dp by dt is equal to minus lambda Lg plus lambda Gx, and x we can substitute. So we get this as gt square by 4. So we get this as g square t square by 4, and this is our lambda gt, dx by dt is our gt by 2. So this comes as our lambda g square t square by 2, and we can combine these two terms. So we get this as minus lambda Lg plus this will be coming as 4 to 3. So So this will be 3 by 4, and we have our lambda g square t square. Okay. And now we simply substitute it in this part. Therefore we get that our n minus lambda Lg is equal to minus lambda Lg plus 3 by 4 lambda g square t square, and these two terms goes away. Therefore we get that our normal force will be our 3 by 4 lambda g square t square. That was asked for. Okay. And okay, we come to the next question. And in this question we are given that a uniform chain of mass per unit length m hangs vertically above a horizontal table, and upward force F is applied at the upper end of the chain, causing it to be lowered onto the table as shown in the figure. Let h of t denote the length of the chain that is hanging freely above the table at any time, the height of the upper end above the table. Drive the equation of the motion of h of t. Okay. So we are given that a certain instant the height of the chain that is above the table is h, and at this particular moment the force is over F, and there is a certain amount of the chain which is lying on the table. And we have to find out the equation of the motion for our h of t. Okay, that is our time dependent function. And so in this case, in the downward direction, we are going to take it as a positive. Okay. And we are given that h is our length of the chain at a certain time. Therefore, we can write that the velocity of the hanging chain that is our v. We can write this as a first derivative of our h, because h is nothing but our distance, height in this case. And from here also we can find out the acceleration in terms of h. Acceleration, that is our a, we can write the first derivative of velocity or double derivative of our h. And so this chain will be consisting of two parts. One part is a moving part, so the moving part will be only this much, that is our h, and rest, this is our rest part. Okay. So we are interested in first of all for the momentum of the moving part. Momentum of moving part, and let us suppose that momentum is p, and this p will be equal to mass of the hanging chain, and mass of the hanging chain, we are given that the mass per unit length is our m, so mass of the hanging chain will be our m times h and multiply by the velocity v. Okay. And now we are going to find out the change in momentum. So we can say the change in momentum, that is rate of change of momentum, change of momentum, that is dp by dt. So this comes as a d of dt mhv. Okay. And This will be giving us our first function. I will be our dv by dt plus second function dh by dt. And we already know that our this first derivative of h is nothing but our velocity. Therefore, we can write this as our mh dv upon dt plus mv square. Okay. And now we are going to find out the forces acting on the moving chain. Forces acting on moving chain. And in this case, we have to remember that we are going to use the formula forces is equal to dp by dt. Okay. Because this is basically variable mass. Okay, so we are not going to use the standard relationship, that is F is equal to mass into acceleration. So let us find out this value of F, which is summation of F. It means number of forces will be acting on it. So we can say forces on hanging chain and the forces on hanging chain, first will be our weight, downward direction. So let us call this as our Fw, which is our mgh, and we have applied force, that is upward. Applied force, and applied force is upward F, that is given in the question, and the sign is negative because in the downward we have taken as positive. Okay. And the third one will be the impulse because of the chain hitting the table. You can say impulse from the chain hitting the table. From the chain hitting the table. And so we can say that it will be having our of two parts. First will be the, because it is going to fall in the downward direction, and so we are going to say that momentum removed per unit time, because there will be some mass that will be removed from the falling chain, and there will be also a contribution because to the upward direction, or we can say upward force on the chain. So this we can say the momentum removed per unit time. Removed per unit time, and that is equal to our mass into velocity, mass flow rate into velocity. Okay. We can say this as our mass flow rate multiplied by velocity, and mass flow rate is our mv, so this comes as our mv times v, giving us mv square, and this is our an upward force on the chain. So we can say that this is an upward force on the chain. So upward will be giving us minus mv square, and then we can find out our net forces, or we can say the summation of the forces is equal to the rate of change of momentum. Therefore we can write that because we have our mgh minus f and minus mv square is equal to, we have this is mh dv by dt plus mv square, and one second. Downward we have taken as positive, so we can write this will be coming as we have here 2mv square and we have our mvh. One second, there is some momentum per unit time. Sorry, so this is a plus, and these two terms cancels out. Okay, and yeah, so this is our the downward. Okay, we got it. And because this will be minus of minus, so it will be plus. And now, okay, we are almost done with this. So we get this as our mgh minus f is equal to mh dv by dt. And we know that our velocity is our single derivative of our height, so its derivative obviously will be our double derivative of height. Therefore we can write, because we are supposed to find out its equation, so we substitute this as our, and okay, so we can say this as dv dt is equal to, we divide by mh, so this comes as g minus f upon mh, which gives us double derivative of h is equal to g minus f upon mh. Or if we can also write it in the form of derivative, so we can say our double derivative of h with respect to time is equal to our g minus f upon mh. So this is the required equation of our motion, okay, that was asked for. And so this completes all the 5 questions. So in this particular all these 5 questions, we have to keep focus on one thing, that the forces formula, more or less directly or indirectly we have solved it by finding out the forces. Okay. So we have to remember that we solved using that the summation of forces, which is our net force, is equal to rate of change of momentum. Okay, we have not used that the force is equal to mass into acceleration. This formula we have not used because this mass is going to change, because it is a variable mass system. As the length is going to change, if you are pulling up, it is falling down, moving from left to right or right to left, this mass is going to change. So this particular formula is not going to used. So we are going to use by using this summation of forces is equal to rate of change of momentum. Okay, so variable mass system, specifically in case of this rope or chain hanging down, falling down, moving in any direction, we have to keep in mind that the summation of forces, this formula we have to use. Thank you, and sorry for once again the stream got interrupted because this some problem with my internet connection. It resets time to time. Okay. But anyways, thank you.